closed captioning. Okay, finally, we would like to thank and acknowledge our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All-Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at the rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay, now I'm going to go ahead and end my screen share, and we'll get started with some introductions. Dr. Eric Hintz will be the one to kick things off today for us. Dr. Hintz is the Associate Chair of the Department of Physics and Astronomy at Brigham Young University, where he's made the very wise choice to study variable stars, specifically delta Scooty variables, a type of short period pulsators, which have been his research fascination for the past 34 years already. In short, Dr. Hintz is an expert, and we're going to be learning a lot from him today. Dr. Hintz, take it from here.
Okay, well, I'm not going to put up any slides to start with here, just kind of give you a little background. Short period pulsator section within the AAVSO covers a lot of territory. It covers everything basically down the instability strip and then off into the maybe even some beta Cephei, some blue pulsators. However, there's a couple subdivisions within that. The Cepheids and the Aurelaries have been the more traditional part of that, this observing section. But now, since I've come on board a little bit, I've pushed to this down to the main sequence where we find the delta Scooties and their much faster pulsations. So the idea kind of behind today was the idea of if you have a couple hours, you can actually do something pretty substantial with the shortest of the short period pulsators here. We're not going to count white dwarfs, but of the instability strip objects. And so I asked a couple of my students to share what they're working on and how we use these very short stars as training tools, because they allow us to do so much in such a short time. But at the end, I will talk a little bit about ways of jumping in and helping on these projects through the AAVSO web pages, providing a target list. So that will be where we end today, but I'll let my two students give you a little bit of information to start with, and then I'll finish up later today. So I'll hand this back off to Lauren to introduce Jarrod.
Thank you. So first up, we've got Mr. Jarrod Hansen. Mr. Hansen is an undergraduate at Brigham Young University, where he studies today's favorite type of stars, short period pulsators. Today, he will be giving us a glimpse into the educational possibilities held by such short period variable stars when they are used as teaching tools in undergraduate astronomy courses. Mr. Hansen, whenever you're ready.
Excellent. Can you hear me well?
Yes, we can.
Great. Okay. And is my screen sharing still working?
Yes, it is.
Hasn't broken? Awesome. So I'm going to have three main sections that I'm going to talk about. First, I'm going to go a little more over the types of short period pulsators that Dr. Hintz just talked about. And then I'm going to go over how we use them for our observational astronomy class here at BYU. And then I'm going to conclude going a little bit more into my personal research and what AAVSO data can do to help contribute to that. So we're going to start off with what is a variable star. So variable stars are stars with periodic and non-periodic fluctuations in brightness. Personally, I like the periodic ones better because if it's not periodic, it's really rough to deal with. So we're mostly interested in studying periodic variability in the delta Scooty region of the instability strip, which, as Dr. Hintz said, falls right down here on the main sequence. So the instability strip is a region of the HR diagram where most stars are unstable. Different areas within the instability strip have different reasons for why pulsation occurs, but in delta Scooty variable stars, pulsation occurs because of a ionized region of helium that causes driven pulsation within these stars. So like Dr. Hintz said, short period pulsators cover quite a few different variability types. So we've got Cepheids, RLRAs, delta Scooties, beta Cepheids, and white dwarf stars. Most of these objects fall along the instability strip, but we have a few, such as the beta Cephei objects, which are bluer objects that aren't quite on the instability strip. So right here is an example of what the light curves from these objects look like. So over an 8-hour period, if you're looking at a delta Scooty variable, which has periods ranging from 1 to maybe 3 hours, this one having a 1.5-hour period, during this 8-hour period of observation, you'd be able to see several peaks of the variable or several times of maximum light, which are one of the most useful things in examining these stars. If you're looking at an Aura Lyra, you'd be able to see 2 clear peaks here, and then you'd start to get a 3rd peak because of its 4-hour period. Cepheids, which are longer periods in the short period pulsator regime, have almost have periods of 10 days or longer. So if you have one that has a 10-day period, over this 8-hour period, it really doesn't change a lot. So that's why we're interested in these very, very short period pulsators, because they're the objects that in an individual night of data, you will be able to see results on. So here are some example light curves of within a 4-hour period using the same periods for delta Scooties and Cepheids of what you'd see. So here in plot A on the left, this is what a curve of a delta Scooty would look like. So in this case, you're taking an observation every 5 minutes or so, which isn't unreasonable for most of the objects we actually observe. So over the course of this 4 hours, you can cleanly see 2 times the maximum light there. Very nicely shaped curve, good clear rises and falls. If you look at a Cepheid, however, over that same 4 hours, if you have the same scale that we're using over here for the delta Scooty, it really doesn't look like it changed a lot. It really just looks like there's a little bit of noise. If you zoom in, you can tell down here in plot C that the brightness is going up. So there is variability occurring there, but you might easily ascribe this to atmospheric effects or issues with your comparison stars, because the difference is just 0.025 magnitudes, which is not a lot. It's not a very large difference in brightness. So these objects are much harder to examine with individual nights of data. You need really long time strings in order to understand these objects. So as a student here, I have had the chance to TA for Physics 329, which is BYU's Observational Astrophysics class. So as part of this class, there are lots of different things that we have them do. One of the main ones is running the robotic telescopes. In the picture right here, that's 3 of the telescopes, along with a beautiful view of the mountains right here in Utah. So we train them on how to use those telescopes and run them using observational astronomy software. And then once we have data, we show them how to reduce, process, and analyze that data to produce publication quality research. One of the main goals for our class has always been to prepare students to deliver and write publication quality research. We also use this class as an opportunity to teach ethical practices within physics and astronomy. So why are short period variables good for teaching observational astrophysics? That's the question we like to answer here today. So the first one is they're a great introduction to many different software that we use in observational astrophysics while providing a clear end goal for the students, as well as data that they can observe, understand, and see without difficulty. So for example, here is a night of data covering about 3 hours that we took on a variable star Atlas 11. The Atlas name comes from the survey where it was discovered, and the 11 is just an internal designation we came up with because we're great at naming things. So here from this night of data, you can see a very clear rise and fall, great signal noise. So this is an object where a student would be able to go in, and even if they didn't know in the star field over here on the left, if they didn't know which star was the variable, they would be able to look around and test some comparison stars and find it. So giving students that opportunity to discover and then analyze these objects is part of what we'd like to do with this class. So as far as analysis goes, one of the main things that we do is we use a period analysis software called Period04. So Period04 allows us to find and fit periods to the data. So it allows us to take the data that we took and use the magnitudes we observed, as well as the times that observed it, to fit a period to the data. So we also use another program called AAAVSO for more specialized observations, but we tend to use Period04 because its statistics are a little more robust. So Period04 will allow us to find frequencies, phases, and amplitudes that correspond to the star, as well as data artifacts. So one of the issues we can run into is not everything we see in a software such as Period04 is going to be from the object. Some of it will come from other sources, such as the way we take our data or errors in our data, and we'll go into that shortly. So here's an example of what these phased light curves look like. So this top plot here on the right, this is the night of data that I just showed you. So with that, we're able to find the frequency, but it's not quite as accurate as we would like. So we get a few more nights of data with a few more times of maximum light, and then we're able to find the frequency really accurately, which gives us a period of 2.89 hours. So once we find these periods, there are a number of things we can have the students do to help them explore reading papers as well as understanding them. For instance, there's a period luminosity relationship for these stars. So we can have them use that period luminosity relationship and then other resources such as Gaia to try to cross compare and examine these objects. We also want to introduce the students to one of the main methods that astronomy is done today. So it's becoming more and more prevalent for lots of research to be done through sky surveys or through surveys that are examining data in extremely large amounts. So we're using that data to help inform us about the object we're interested in. So one of them that we use frequently is the Assassin Supernova Survey. So its prime research mission is to search for supernova, but as part of their data analysis, they do return a section of observations for variable objects. So if they can examine it and find a period, they will report it. And we've examined some of these stars as well as stars from other surveys to compare how their periods that they found match up with the ones we see. The reason we're doing this is to try to understand how cadence affects observations. With sky surveys becoming more and more prevalent and the amount of data we're receiving from sources like these skyrocketing by orders of magnitude, we want to come up with ways that will allow us to look at the data and then see what we can legitimately say about the data without having to have hundreds of grad students dig through the millions of objects Assassin looks at. Another survey we use is the Atlas survey. So The Atlas survey is a supernova looking for near-Earth asteroids to try to search for objects that could potentially hit Earth. And similar to Assassin, they also report on variability objects, and you can access this data. And we've done that to compare with data we take here. So when we analyze this data, we can see from the top two plots, this is the phase diagram that I showed you earlier. So these are the phase plots, which basically show with the frequencies we found, how well does our data look? And both of these look very well, very good. The lines are very clear. There's a little bit of spread, but overall it looks really solid. But then if you look at the frequency analysis, which are the two plots on the bottom, you can see using our high density data of observations taken around every 5 minutes over the course of the night, we get clear frequency peaks that correspond to the harmonics of our initial frequency. So we're not just seeing one frequency's peak, we're seeing others that help confirm our observation. It helps show that our data is actually real and not some sort of artifact. Looking at the Assassin data, we don't see that. You can see there is a clear peak right around 10 that corresponds to the same frequency that we found in our data here, but you don't get any of these secondary peaks that help confirm the object. If you look really closely in between the noise, like you can tell yourself you see the second one, but it's barely above background and doesn't tell us much at that point. So this is one of the issues with cadence is when you perform a period analysis, you don't get a clear as of a result as you do with high density data. So as part of our research, we were interested in what medium cadence data would do. So we looked at data from the Kepler survey and the TESS survey. So both of these surveys are searching for exoplanets. And as part of that, they take data in most regions for TESS at a cadence of around every 30 minutes. And Kepler has a similar cadence in most cases. So this is in between the cadence that we have of maybe 5 minutes, but much faster than the cadence that Assassin or Atlas has, which they're getting a data point every couple days. So with this, first we'll look at the Kepler data. So with Kepler, you can see we do find the same frequency. We do get the same phasing that we did previously, but there does seem to be a little bit more of a spread in our data. So in this case, Kepler shifted slightly on the field it was observing, and our star moved slightly into another pixel that had a different error. And if you notice here in the middle, there's a slight downtrending in our data, and that is actually causing this broadening. So we're working on reducing data artifacts like this so that we will be able to use this data better. So surveys like this are good, but you do have to be careful for data artifacts that might not appear in your regular data because of the way their observations are taken. TESS presents a whole nother problem. The biggest problem with TESS is its problem of scope. So looking at this TESS field here on the upper right, it covers about 10 degrees of sky on both axes. Our telescopes here don't cover anywhere near as much. So if you look at the little green box that I put here on the screen, that corresponds to the box here on the bottom of the screen. And then in that box, we have another green box that actually corresponds to the field we're able to observe. So TESS frames provide us with lots of data, but it makes it really challenging to try to sift through without getting lost. It's hard to find this. And then TESS data we can find, we have on the left side, this image over here that shows what our observations saw. The first plot is a delta Scooty in blue, and then below in pink is actually a variable star with a 3-day period. So it's able to show up much more cleanly in tests because of its cadence. So the period of your object relative to the cadence is one of the big deciders in what your observations will be able to do. So going forward, we want to take all of this understanding we've gained from looking at all these surveys and figure out what we will be able to do in the future with LSST or the Brigham telescope, because LSST is going to generate millions of hits every night. I believe the current estimate is about 10 million objects that could be variable every night. And there isn't a reasonable way to follow up on all of these. So what we'd want to do is we want to find some way of reducing that number of objects that it flags into something that's manageable, that can be followed up, not just with telescopes here, but also with telescopes at from the AAVSO and other resources. So we're taking data with our telescopes here at BYU to help improve the data we've found from surveys so we can more completely understand what's happening with variable stars. So as part of this, what could AAVSO data do? So observations of just a single night, as I showed earlier with the periods of delta Scooty stars, will be able to show several times the maximum light. So even if you're observing for just 4 hours, you might get 1 or 2 times the maximum light. One of the biggest disadvantages we have from our observatories that we control at BYU is all of them are here in Utah. So that means we're observing them at very similar times from all of our telescopes, leading to data artifacts because of Earth's rotation. So something that AAVSO data would do is it would extend our baseline around the Earth and across the continent and let us remove some of those data artifacts because we're no longer taking data at the same latitude. It will also provide coverage of more objects because BYU is located at a longitude of +40. We can't observe basically any of the southern sky, or if we can observe some of these southern objects, they're not up for long enough for us to find whole periods. So data from AAVSO would allow us to cover more of these variable objects that we can't study here. For instance, Assassin, 74% of their variables are in the southern sky. With other large telescopes, bigger than the ones that we have here, you'd be able to obtain higher density curves, which helps us constrain the systems better, as well as allows us to analyze them in more depth. With more telescopes than we have here, we just have 4, we'd also be able to get these high density observations on more objects and then further constrain our systems. And with that, I will conclude. Thank you for listening.
Thanks very much, Mr. Hansen. Okay, next up, we're going to be hearing from another undergraduate at Brigham Young University, Mr. Marcelo Bighetti. Originally from Brazil, he moved to the US to study at Brigham Young, where he's majoring in physics and astronomy with the addition of high school teaching credentials. It's this educational perspective that he'll be bringing to us today as he discusses the misconceptions that high school students have about astronomers and how short period pulsators could be used as a tool to combat misinformation. Mr. Bighetti, please take it from here.
Okay, thank you. Can you listen to me and see my screen?
Yep, we can see your, okay, now it's full screen, excellent.
Okay. Hello everyone, good morning, good afternoon, good evening, whatever you are on the planet. So me and Dr. Hintz, we decided to create this competition among all the high school. We start here in Utah and probably will spread this all to US. So, but I was talking to many, I visited many high school, talked to many students, and I start seeing a kind of pattern. So they what is astronomy for them? And due to COVID, I had to stop visiting school, and I did a kind of survey with, it's not an official survey, but I asked with my friends, hey, can I borrow your kids? I just want to send a questionnaire. So I sent this questionnaire to 209 kids from junior high to high school. So this is a kind of overview, and most of them is here from Utah, and this is more girls than boys that had answered the questionnaires. And I made some initial questions for them. So, hey guys, do you like astronomy? Yes or no? So 100% of them say, yes, I love astronomy. Second question, do you like math? Yes or no? Guess what? 4% like math. The others, oh no, I hate calculus and mathematics. Hey, do you like physics, guys? Do you like? Yes or no? Guess what? Yeah, not much. Yeah, I don't like a lot of calculus. And I start thinking, okay, what do you relate to astronomy? So I made a lot of questions. In fact, it was 42 questions. So don't understand wrongly this. This is not the answer to the ultimate question of life, the universe, and the everything from the the Hitchhiker's Guide to the Galaxy. It's not from that. It's just a coincidence, or maybe it was on my subconscious. So 42 questions, and I showed them a picture. So hey, is this relate to astronomy? Oh yes, of course. And is this related to astronomy? Oh yes, it is. And I showed this graphic, and they start laughing. It's not. It's just a graphic. And I show this. It is related to astronomy, my friends. And yep, it is. And I showed this beautiful formula, and it is related to astronomy. Yes. Maybe not. So what are the results with this 209 young people? Unfortunately, 95% of them think that astronomy equals astrophotography. So, oh, okay. And who can we blame for this misconception of astronomy? And I go deep in the questionnaire, and I say, no, astronomy is not astrophotography. It's just a little tiny part of it. So we don't have a lot of science in those beautiful pictures. Little, but not that much. And okay, now what? What are the causes? Who we can blame for this misconception? All right, so the first one I see is the social media, the news, the journalist is related to the news. So we are guilty as well, the family, the friends. And also, unfortunately, I see that they are complaining about academic arrogance. And we'll go through all those three in details. The first one, social media. Today, the young people and all of us, we are over, what I can say, we are receiving a lot of information, more than we can absorb. So if you type astronomy on social media or on Google it, what you can see on Instagram. So you will see beautiful pictures. Okay, and Pinterest. type there astronomy, a lot of big and wonderful pictures. Even on Facebook and in astronomy magazines, most of the articles of the posts, we have these beautiful pictures. So day after day after day, okay, astronomy is related to these beautiful pictures. And if you type astronomy on Google, probably you will not see, or even if see, you will ignore, if you are a teenager, something like that. Search for exoplanets around Pulsating star of AF type in Kepler short condensed data in the case of KIC 819F61. So what the heck is that? So you don't see something like that. Oh, sorry. Probably you have to go 3, 4, 5 pages on Google and to start seeing something like this. This is a paper, right? And the journalists and the news, there is a problem. So when a paper is published, maybe the journal, oh, I need to read it and to translate to our language, not the scientist's language. So for example, last year about the life in Venus, the New York Times, we have this headline, life on Venus, astronomers see a signal in its clouds. So if you read that and you don't care about reading the paper, so, yeah, there's life on Venus. And then later you say, oh, disappointed because there's no life on Venus. It's just some kind of signal and blah, 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 blah. So I see that the students, they start getting disappointed when they go deeper, and astronomy is not just beautiful pictures. There are a lot of calculations, there are a lot of interpretation, a lot of data to be reduced and analyzed. And they, oh no, I don't like that. And on the other side, many students who love calculus, who love statistics and interpretation of graphics, they don't see that astronomy has that. So we are losing a lot of good students from both sides. The side that they love calculus and whatever, and those that like only pictures. And one of the purpose, the goal of this competition is to open the eyes of these young people. We need more scientists, we need more astronomers, but we need to do our part, okay? And this is a joke. On April 1st, talking about social media. On April 1st, Fool's Day, I post this on my Facebook timeline, and I say, oh guys, I'm studying at BYU astronomy. Okay, I decided to be a flat earther. And you have no idea, I have hundreds of comments, and many of them, many people believed that I believe in a flat earth. And then the April 2nd, I add an observation. Hey guys, this post from yesterday was just a joke from April 1st, Fool's Day. So we are open to see a lot of things, maybe fake news, even in the science, not by intentional, but just a kind of interpretation. Okay, so why families and friends are responsible for this kind of misunderstanding, right? I remember it was 1989. I decided to go to college and study physics. As soon as I made this statement, my family, relatives, friends, dogs, and dinosaurs, everyone say, what are you going to do with physics? Do you want to be a mad scientist? So but I love calculus, I love mathematics. Go do anything that will be more word for you, you earn more money. And I say, okay, I was really young, and you start following the crowd. That was one of my big mistakes in my life. So I decided, okay, let's study economic science. And I hate it anyway. And also the families, father said, oh, I'm a lawyer, I'm a doctor, I'm whatever. I want my son follow my path. So this is really good. This is not good. This is the opposite. We need to cheer up the people who want to be a scientist. We need those. Yep. And the other one, the students share with me this kind of arrogance from professors, from doctors, from whatever. They say that not all of them, of course, but we must think about this, because in the point of view of the teenagers, sometimes this arrogance that you know everything and they don't know nothing, this is a problem. Even the way the teacher is teaching is the problem, and they say, I don't like it. And now I think I don't put all the details of my survey here, but I think it's a half of them. So they prefer to watch a YouTuber to teach them physics than the teacher. So it's a kind of, this YouTuber rock stars, and just, yeah, this is a problem. Now, let me talk about the competition. I will not go to details because my friend Jarrod already talked about that, so it's not necessary to talk about this. So what we are going to do, I have been in touch with many principals here in Utah, and they are really excited about this competition, and they are willing to help to put this in practice. So in an overview, we will have 4 parts, but why short period pulsating stars? I think Jarrod was really good, explained why. I call the elegant curves of those stars, and then a kind of easy interpretation. And with data on one night, we have a lot of data, and they can start working on it. How the competition will work? Okay, the first phase, we are going to teach the students how to use the tools, the softwares, and everything. Okay, you use this software for this, blah, blah, blah. When I think we'll be together with the data. So, but it's another kind of data. The data number 2 here is the data that we will provide them for the competition. It will be the same data for everyone. Okay. All right. So the students got those data. Sorry, my voice. What are the good results that we have from them? And many students already are excited to do this. So it's a competition, you know, human being is moved for competition, especially when they are teenagers. Many of them already are expecting, waiting for our competition. And for today, I would like to thank you very much. Why should I add a question mark? Oh, sorry about that. Thank you, Lauren.
Thank you. Thank you, Mr. Bighetti. Sorry about that. I had to find the unmute button. Okay, next up, we will have Dr. Hintz, who's going to be talking about some of the scientific side of things. And I've already introduced Dr. Hintz earlier, so I'm just going to go ahead and hand it over. Dr. Hintz, please take it from here.
Okay, let's see if I can get my, okay, I got my slides up. Lauren, do I have my slides?
No, I don't see them here.
Okay, let me go back and share my screen again. Okay. I had left it partially open, which was not a good thing.
Yeah. Okay, now I see your slides. You can go ahead and put them
Okay,
in.
and then we go to pop it open. Okay,
Perfect. Thank you.
couple things here. Just in terms of the competition, this is kind of the first cut. It's taken Marcelo and I a little while to get to this point. But I've also talked to Stella at the AAVSO and some other ideas. So as this grows, one of the possibilities would be that each school would have a different star, and that members of the AAVSO could, in a sense, adopt a school and help them with data. Stella informs me that a lot of you observers are rather competitive and might actually enjoy doing that. So just know that this is something that's evolving. We're just kind of doing a preliminary. Some of the judging we're looking at is kind of modeled after musical competitions that I'm used to going to since my kids were all in marching band, in terms of, instead of ranking, giving a grade, a superior, an excellent, a good kind of thing. Eventually, maybe you would get to something that's very competitive and actually rank the schools, but as a starter, trying to reward them for their best efforts. And when I was trying to put this together, the rest of this time, and seeing what the other two are presenting, I thought maybe I'd go back to something that I run into a lot. The question I get from the research I do. As was mentioned, I've been studying delta Scooties for 34 years. When I was an undergraduate at Case Western Reserve University, I did a research project, which was rare back in those days. Some data that a graduate student had left over, and it just happened to be a delta Scooty. And that's kind of set a lot of my real interest, my main interest in my research for a very long time. I got deviated into large scale structure of the universe for my PhD, but I've since come back to the variables. And the question I always get, and I thought might be worthwhile to talk a little bit today, given what both Jarrod and Marcelo talked about, because the students are going to ask that, both our undergraduates and high school students and anybody else. Why do we care about these objects? Are they just interesting? Do we just want to know the period? Is it worthwhile observing them? Why should I take data? That's kind of a question from an AAVSO perspective. Why would I want to take data on this? What good is it going to do in the long run? And then, really what's going on here? What are these stars? Why are they doing what they're doing? And I thought I would kind of go back to that a little bit and then come back around to our observing program and how we can use a lot of data help in the long run on these objects and what they're useful for. So I'm trying not to get overly technical. I'm going to have some equations up here that are going to be, like Marcel was talking about, some of the equations that scare people to death. But just giving you some idea why we care about these objects and what we can learn from them, and try to do a little bit, some analogies, so maybe it makes a little more sense in some ways. So first off, let's find my favorite little stars here. And a lot of the short period, the SPP observing section is right down this instability strip line, with a lot of the Cepheids up top, the Auralaris, and then the delta Scooties down in the bottom. And if we extend that down, we could pick up white dwarfs, but that does get to be a little difficult to observe because they are small. So we're gonna, again, I'm just interested in the ones down here on the bottom, and we're gonna see this graph to the right-hand side come up again, and you're seeing something down here, some Gamma Doradus that haven't been mentioned, but I'm gonna mention them later. And then here's our Delta Scooties, and we're gonna kind of explain what all these crazy letters and numbers mean under here. If Jarrod's still watching, he's gonna get a review for the final exam for class when through this. So one of the things we start doing, I've been teaching for quite a few years, is the graduate and now the undergraduate stellar astrophysics classes. And one of the things we talk about in there is the models of stars, basically running all the various things you can think about: temperature, density, pressure at each radius inside the star, or we kind of prefer it if we run it in terms of mass shells instead, because mass is something that's kind of fundamental to a star where the radius will change. And you see these equations that tell us about the run of each variable. So how they change through the inside. Now this has to be solved on a computer. There is no analytic way to solve this. You actually have to take guesses and then try to get a good solution. So stellar modeling is very interesting, and we get a model. So we build a star on the main sequence, and we know the internal structure. And that gives us a lot of information, well, at least from a model. So we have these models that tell us what the inside of a star should be like. Now, if you walked outside and looked at the sun, please don't do that. Okay, don't look at the sun. But when we look at details of the sun, we're seeing the photosphere. All these modeling pieces are on the inside. We can't see in there. So that's kind of an interesting problem. How do you check whether the models make any sense? Okay. Well, turns out that the really short period pulsators, the Delta Scooties, and some of their relatives can contribute to this. So there was a first approach at trying to understand the pulsation of stars. We've known about pulsators since the very end of the 1500s with the discovery of Mira, so the long period pulsators, and then moving on from there to the discovery of Delta Cephei, and then so forth through all the other variables. And so the astrophysics people wanted to say, well, how can I model this? And what they did is, let's look at this second line here. I'm going to go quickly through this, so don't worry too much about it. So this is the radius as a function of mass. So where is each mass shell? And this R0 is what is the solution for a stable star. And then the idea here is we smack the star and see what happens. It's like take a hammer to the star, smack the star, and let it ring and let it vibrate. And so that's this omega here is basically sine waves. So we'd hit the star, it would shrink and expand, and we can model that. And you get all these crazy equations that come together, making all these assumptions, and you get a very common physics solution to this. Some of you might know this terminology of the Sturm-Liouville problem. It is a very specific structure. But if I look at this, it says there's an infinite number of pulsations that can happen in the star. That's one of the solutions. Now this is radial, and it's assuming that once I smack it, that it'll just keep going, which isn't very likely, but it was a first cut. It was a first try. And what we find is we have a lowest frequency in this model, which we're going to call the fundamental. And that's kind of like a specific pulsation, a specific radial motion of the star that goes with it. We say no nodes. So this is basically where the entire star goes out together, entire star comes back together. All the layers kind of go in lockstep. Well, what's interesting about this, now astronomers and acousticians, so we have a fairly substantial acoustics group here at BYU. And if I talk to them about this, it turns out astronomers have everything off by one step. But we're going to stick with the astronomy definition here, just because that's the more normal. But the terminology is similar to what we'd have in acoustics or music. So if you've played a musical instrument and you think about the note, there's a flute at the bottom of the page here. Basically, that's because that's what I have at home. And although it's been stolen by my daughter, my flute. But I used to use that when teaching, to play a note. But when you actually play a note on an instrument, it's not a single note. It's a frequency and then it's multiples. So you have the harmonics. And so after we get the fundamental, then we have a sequence of harmonics. And if you think about musical instruments, every one of them has a different tonal quality. It has a different sound. Even if I'm playing the exact same note, so I'm playing a middle C on every one of the instruments, an oboe, a clarinet, a flute, a trumpet. I'm playing the same note in theory, but why does a trumpet and a flute sound different? What is the difference? And it's really a matter of where the frequency, what's the dominant frequency? And maybe it's not the fundamental. It might actually be one of the overtones. So now some instruments actually run in different overtones anyhow, but the idea being that a flute is kind of the main note is the fundamental, and then we have the overtones from there. If I look at the top, in the graph to the top right, maybe, the clarinet, there's a possibility that it's skipping every other overtone. So the fundamental, and then we're getting the second, fourth, fifth, sixth, eighth, 10th overtones. And so clearly a flute and a clarinet sound different. Or something where it's actually maybe an instrument isn't playing in the fundamental, maybe it's playing in an overtone. Well, it turns out we can do this with stars. And the terminology is going to carry through for us. The idea of the fundamental and the overtones. And that's going to be a little fascinating. So in the end, what we're almost going to say is this a flute star? I know that sounds really kind of strange, but does it have a frequency content that maybe is like a flute? And we do see some stars where this is actually not a bad description of the amplitude of the different frequencies within the star. There are stars we're going to later on that we might say are first harmonic pulsators or second harmonic pulsators. And so even within the delta Scooties, there are unique groups. But this was based on the internal structure of the star. So if I can actually map out the frequencies in the star, I can map out the internal structure. And if I can do that, I can compare with the models. So this is classic science. We want to be able to model something and then come back in with observation and see, is that correct? After the first step, the adiabatic solution really doesn't work. What really, Arthur Eddington worked on this back in the mid 1920s, and taking it kind of the next step where we actually, the idea that if you just hit the star and let it ring, it would damp out. So something like a Cepheid he thought would stop after, now of course this is a long time, 8,000 years, but due to damping. So if you get this upper right figure up here, we have a decaying oscillation. So a damped oscillator, which is what would happen. So if you take somebody on a swing, pull them back, let them go, and if they don't pump their legs, don't do anything, the swing is just going to damp down. So the non-adiabatic pulsation is where we actually have to put energy in. So as the person swings back on the swing, we push them again. They go through a cycle, they come back, we push them again. That's the non-adiabatic here that we want to more realistic star looking at it. So if that's the case, in the adiabatic case, we don't allow any heat to move around. We don't allow energy to move around. But now we are going to allow some of the energy being carried from the inside of the star out to be absorbed. So at a given layer in the star, it gets absorbed. Well, if it gets absorbed, that energy is going to want to push the material outward. And so this absorption of some of the energy coming through the star is going to want to push the layer outward. And we're going to go through how this would work. But if I look at this equation down here, this is actually the change in heat within a given layer. And the only reason we're interested in here, the reason heat can change is if the temperature is different. And that's important to this. Or this line, this second middle term, F is the energy of the light passing through the star. M is the mass of the shell where it's happening. And we're going to talk about this. Well, it's a K here, but it actually should be a kappa. This is something called opacity. Some of you probably have plenty idea what that is. Others might not. We'll talk about that in just a second, because that is a fundamental characteristic in stars. And why it takes so long for energy from the center of a star to get to the surface. And the last piece here is energy. So these are ways that we can change the energy within a given shell within the star that might cause pulsation. Any one of these could potentially be the push on the swing. In the end, we're going to focus on this middle one. The one to the left, the energy generation, is something we see in dying stars. You might have, if you've been to some other seminars, you might have heard of thermal pulses in some of the very large stars that are ready to shed their envelopes and become planetary nebulas. That's more related over here. So we want to look at this middle possibility as driving our stars. So now we've talked about the harmonics, and those would damp out over time. Now we're going to see if we can drive them so they're stable. So if you think about something like Myra, since about 1596, it's been constantly observed and it's been pretty stable in its pulsation. So it's been doing the same thing for a long time. How is it driven? How are all these driven? Okay, so the first thing here is, well, Arthur Eddington's idea for how these stars pulsated was called a Kappa mechanism. So this was a change in opacity. It would be like if we had clear windows that let all the different light through and we can see what's outside. We're not absorbing any of the light. We're just letting it pass through, versus something, maybe not the best example here, but something where I'm not seeing all the light through. Some of the light is absorbed by the glass, the material. Well, and that's what the interior of the star does. Depending on the conditions, the atoms within a given layer will absorb some of the energy, some of the photons. And so a very logical assumption for how pulsations could work came from Eddington here. He said when a star is compressed, so the idea here is we're going to hit the star, say with a hammer, we shrink it down a little bit, so we compress it. And then his assumption was then if we compress it, the opacity gets higher. And so what that means is it blocks more of the light trying to go through. We might say it becomes opaque. You might see this in if some of you wear glasses that change when you walk out into the sunlight, they become more opaque. They let less light through. Well, that's kind of the idea here. If the opacity goes up, more of the light is captured. and that energy goes into the material. Well, that trapped energy then pushes the layer out, and as it expands, it gets less dense, and eventually it'll become more transparent. And then all that energy that was trapped can be released and head off to the surface of the star, and gravity pulls the layer back down. That was Eddington's model. And for the most part, it's close to what's actually going on in these objects. One problem here, and that is actually, if you actually look at these, one of the lines has a problem in it. And in the end, it's going to be our top line. When the star is compressed, the opacity goes up. Well, if we think about gas, if we compress gas, we tend to drive the temperature up. If we drive the temperature up, the opacity is actually going to drop. Just the nature of opacities. And so his original assumption that when the compression happened, that the opacity would go up was actually wrong. And because of that, the Kappa mechanism doesn't work. If the Kappa mechanism actually had worked, just about every star would be a pulsator, which would make trying to find a stable, make AAVSO even more interesting. Every star would be a variable to work on, but that's not the case. We've shown that they're in kind of in the instability strip here. So we have to move on to something here. The issue here is opacity does not go up under compression. It actually goes down. In most layers of the star, it would drop under compression. So the idea that Eddington had is pretty much correct, but the physics was off just a little bit. And so it's really trying to figure out what about opacity could do this? What is there something else we have to add in to the situation here? Well, yes. This is now called the Kappa gamma mechanism. So it's actually two things going on. We're going to compress the gas. Well, what we have is a region here. So if you're deep in a star, the material is all ionized. It's so hot deep in a star that all the electrons have been kicked off of the atoms. As you get near the surface, a lot more of the atoms still have their electrons. Partway through the star, you're going to get a layer where you have a combination. Some atoms have their electrons, some don't. So this is called partial ionization. And this turns out to be the critical part. And this means there's a specific region in the star that is activated. So as the gas is compressed, instead of the energy going into raising the temperature of the gas, it actually goes into ionizing the gas. So now basically the density increases, the opacity increases. Now I drive the material outward. So that was the real major step, is we had to have a very specific region where this would work. And then on the expanding side, we have another part that instead of the gas, you'd expect the temperature of the gas to drop during expansion, but it doesn't, because it's getting energy from electrons recombining with the nuclei as it gets further out. And so this is the mechanism that is driving the stars. What makes that important is this is why not all stars pulsate. Only certain ones do. And let's go right to this. So the helium, hydrogen and helium stars, ionization zones. So basically a hydrogen with an electron, helium with 2 electrons, about 10,000 Kelvin. This is a place somewhere in the star this layer exists. This may have been brought up if the long period variable session has talked about it. This is the mechanism driving those stars, the long period pulsations. Here's my favorite little guy right here. So this is helium that has already lost 1 electron. and the second one's starting to be removed. This happens at about 50,000 Kelvin. These are the stars of the instability strip. So this is the Cepheids, the Aralaris, and the Delta Scooties. And the period of pulsation then is based on the density. Then we get this goofy one here. I'm just going to mention the iron one. So there's some iron ionization at about 200,000 Kelvin that is actually responsible for some other short period pulsators called beta Cepheids that we're not really even talking about here. So now we talked about this idea of what frequencies might be in the star. We know the mechanism now for driving this, except there's one, we've talked about adiabatic spherical, which is where we got the terminology. This is non-adiabatic spherical, where we talk about the ionization zones. And then people added one more complexity to it, and that is a non-radial pulsation. So that sounds funny. That's something we're not used to, the idea. It's easy to think of a star expanding out and contracting, expanding and contracting. But what we have here is some really strange equations that I was not even going to try to put on a slide. I actually have to give this lecture on Monday, so Jarrod's going to appreciate that. But about the full mathematical version of this. But when we get it, I'm going to skip a whole bunch of steps and jump to the solution. This is a slight bump of it, but not radial. And so it is possible to set up these rather interesting perturbations, so changes on the surface where one side of the star may be going out while the other side's coming in. So it's almost more of a sloshing around the material, or you have two pieces going straight across from each other moving out while the other two sides are coming in. These are called the spherical harmonics. And if you look at the site like astroseismology.org, you can actually see some of these modeled and see the patterns. Now, the reason why we bring these up with the very short period pulsators, the Delta Scooties and also the Gamma Doradus stars, is these are frequencies we can find, and they are limited by the internal structure. And so this is one of the ways to start probing the inside. Okay, so that's what makes this so important to us, is that idea that we can actually study the inside of the star. Very quickly, there's a couple of different frequencies that if you do stellar interiors, you run into. One of them relates to convection, which we're going to label as an N. And then we have one labeled as S that is related to sound velocity. So the N is basically down near the convective layers. It's the force. If you bump a layer of the star, it's basically a way that gravity will pull that layer back down. So this is right at the edge of where convection would happen. And so what happens in a non-spherical case is we get this funny solution, and N and S both have to be just right for us to get pulsations. And I look at this and go, that's way too complex. Let's skip to the punchline. There's something called P modes. These are related to the S frequencies, the speed of sound. These are sometimes called pressure modes. And so this is, you'll hear this phrase, you'll see this phrase quite a bit, P mode pulsators. And if you come over here, Delta Scooties, there's this radial, this R, this capital R is for radial. That's what we've talked about before. And then pressure modes. So these are the types of things we see in Delta Scooties. These are what we'd also call acoustic waves, because they are based on the speed of sound in the material. And that's something we actually can measure on the interior of a star. These tend to be high in the star. They're above the level of the fundamental pulsation. Then we have something called G modes. These are deeper in the star and related to the buoyant force part of convection. And if you come down here, right below, so you have the instability strip here, the two lines coming down are the instability strip. And you have the main sequence at the bottom of that. And right below the red edge of the instability strip, you'll see the gamma doratus. And these are G mode pulsators. And being able to differentiate those takes a fairly good data set. Usually you want observers scattered around the world. You want a lot of coverage in a short time to kind of separate. Is this a G mode? Is this a P mode? And I will mention that there are a handful of stars that are actually considered hybrids, where both pressure and gravity modes have been found. So it really comes down to, why do we really care about the really short period pulsators? Well, some of the answer to that is they are fast. They change quickly. And because we have a lot of cycles in a short amount of time, we can really go after the frequency content. And we can maybe tell the difference between a flute and a clarinet in that sense. So this is the astroseismology. Sometimes this is the ringing of stars. And by examining the frequency content, we can look inside, gives us a probe of the internal structure. This is a place where both period 04 and Paranso are very useful to us in removing those frequencies. But one of the big advantages here is if you have observers scattered around the globe that can get on the target, you can actually get your kind of false alarms removed. Your frequency analysis is much sharper. It's kind of why the data from Kepler and some of the other satellite systems, Corot, MOST, those systems were so strong. But you'll see this done in short period pulsators because you have to get enough cycles to find all the frequency content. So because there's stars that we can get 7, 8, 9, 10 or more cycles in a night, we can get some that have 24 cycles in a night. That gives us enough information to start looking, getting enough of the frequency space. For a long time, this was very difficult. The maximum number of of frequencies and cross terms found was on the order of 30. Now with some of the satellite systems, we've gotten out to about 180, I think is the last one I saw, individual frequencies found in a star. The second thing that makes these stars, really useful to us is the fact that delta Scooties have a period luminosity relation, just like the Cepheids, and likely it's a bit tighter than the Cepheid relation, and it actually is an extension of the Cepheid relation. It comes right on down the period track. The trouble is with the delta Scooties, we just can't see them at the same distances. And the last reason we really want to study these stars is the fact that, every time I get into teaching an introductory astronomy class, one of the first things I say is, we can't watch a single star evolve. Well, that's not necessarily true. For the fast pulsators, we have enough information. If we can watch them enough, some of them will actually start showing signs of evolution. And so actually being able to see a star change in our lifetime and over a few years is rather shocking. So we look for subtle changes in the period of the pulsation, the amplitude of the pulsation, and even some phase jumps that can occur. So these kind of things, we need to get enough observations to be able to see the subtleties and the details. One of the neat things about Paranso, the latest version that just got released fairly recently, we updated to it not that long ago, It's really good at measuring times of maximum light, but one of the cool things it can do is it can pull data straight out of the AAVSO website. So if you wanted to play around with some of this information, it's kind of fun. I've actually done it with some Cepheids as well as some of the Delta Scooties. So that's kind of a neat tool that crosses over AAVSO with some other software. But those are our three main ideas. Well, to do really the top and the bottom one here, which are the ones that interest me, particularly the stellar evolution is kind of my favorite. But to do number one and number three takes time. It takes a lot of observations. It takes a lot of effort. And the problem is, which star do you choose? Which ones do you call everybody? Which ones do I put on the AAVSO website and say, hey, everybody, jump in and give me a couple hours and go get a light curve of this star? How do I pick them? How do I actually make that selection? I'll tell you, well, some of the idea here is, Jarrod showed you some of this. This is our campus facilities, and this is what we use a lot of this. Every clear night we can, we're getting light curves. You will notice a couple, there's an extra shed in this one picture. So there's a shed to the right-hand side and there's a telescope to the right-hand side. The telescope to the right-hand side has since been removed and being replaced with a bigger telescope. And the shed is going to have a new telescope in it that I'm really, really looking forward to as soon as the semester's over and I can install it. The picture on the top left is also a telescope I dearly love. This is our new 24-inch on the campus dome. But just for those later people that can look at this, if you want to later, all the different telescopes on campus. So this is what we can have our students using and working with, and can provide tons of data, but it's single longitude data. And that's a problem. That gets aliases in the data. So if I can get a lot of help from other people, or other people that like to work on these kind of stars can get help from observers all over the world, we can do a better job doing the astroseismology and doing the evolution of these stars. I have nothing against RLRs and Cepheids, but Delta Scooties definitely are the ones to do this with because they show things so much quicker. To help us out with a little bit more data, we do have BYU's West Mountain Observatory, which is just down the road here. I don't know if Mike's on here or not. Mike Joner watches over that place and has developed quite a bit up there. He might actually be up there right now working on it. But there's a 36-inch up there, a 20-inch, and a 12. And then I get quite a bit of data from the Dominion Astrophysical Observatory in Canada, which is the pictures to the bottom of the screen, bottom left. This is spectroscopy that helps us narrow down some of the photometry. And we also do spectrophotometry, which is a little different. And finally, the 1.8 meter, we're working down at about 17th magnitude right now on some of these targets. That's probably out of most people's range. But I have targets all the way from visible in the night sky to 18th magnitude right now that we're chasing. So I can provide targets for just about anybody's telescope. The neat thing about the 1.8 meter is this last piece, the spectral polarimetry. We are going to do some work in measuring the surface magnetic field of these stars as a function of their pulsation. What would be really nice is when we are scheduled to do that, is if we could organize people to take simultaneous photometry. To do the spectral polarimetry on a 1.8 meter, I'm looking at something on the order of probably a 7th or 8th magnitude star. So I figure a lot of people can jump in there. And then finally, BYU has bought into the ARC consortium down in New Mexico, which is the picture on the bottom right. And this is a 3.5 meter that can also provide information. However, that's still mostly in the Intermountain West. DAO is just a little bit further to the west. And so we don't have a lot of coverage around the globe. And that's where we can get some help with people. Jarrod's talked a little bit about Atlas and the data strings here. To give you an idea, here's the longest night from Atlas on a single night of this star. This was our first light observations for the 24-inch. This is the first night it was running. You can kind of see it's a very different looking light curve from what we had to what is over there. And just some other examples of some data that we've taken. But what I want to show you here in the end, I just should mention these. Got to thank Mike for these. This is data from West Mountain. And this is helpful to show some ideas. Notice the peak of these curves in the bottom. So the minimum light, maximum light. These are not at the same height. So stars can pulsate in one frequency with its harmonics or multiple frequencies with their harmonics. And the case in the left here is one that's clearly got a second frequency in it, a second range of information. So you get a beat frequency. This one's even crazier. The one to the right, one night you can see that it's higher amplitude than another. So this one has a really strong beat frequency to it. And this is the kind of thing we have to have a lot of coverage from a lot of different people to see that. So why do we, or where can you get involved with this? If you're interested in observing, well, right now, from the Atlas survey itself, we have about 1,157 northern targets, add about another 1,000 southern targets for monoperiodic, so single frequency, add another about 1,500 between the north and south for multi-periodic ones. And then there's a group called the sine wave ones, which is about 23,000 targets. These range from probably 10th to 18th magnitude. We observe the 12 and a half ones on an 8-inch telescope. So that's all you really need with a good CCD or CMOS camera on it. We've got another 5,000 that were discovered in the KELT database. There are a whole bunch of other surveys where they found variables, and that's the only paper on the object. These run upwards of 6th magnitude. We have a 6-inch telescope we use to chase those. So basically it means somewhere on the order 25,000 targets. I am a little shorthanded on telescopes. I don't think the university is going to give me enough to cover 25,000 targets. So there'll be opportunities if people want to jump in and spend a couple hours. And got a couple hours on a target, get a single light curve or multiples if you want to go longer. And we can pare down that list of 25,000 to find the best ones that might be useful for astroseismology, might be the good candidates for studying stellar evolution. Not all the stars show the stellar evolution, so there's only a fraction of them. And some of the question is why? And so these are all things we can address by chasing after these delta Scooties. And I meant to have this done, but my responsibilities as associate chair, the chair keeps apologizing for walking in my office all the time with questions. But I haven't quite got the list put together. But basically looking at a list of targets from here that have had very little observations done on them. A group for the Northern Hemisphere that goes all through the year, a group for the Southern Hemisphere that goes all through the year, and over a wide magnitude range to try to accommodate everybody's telescopes. So those should be, I'm hoping early in the summer here, or spring, to actually have that off to the web people at the AAVSO to put that into the SPP website. If you want to jump in and help us with a couple hours of time, and maybe even help out the high school students and undergraduate students as well. And so I've got to always throw up the acknowledgements. And with that, I will throw it back to Lauren to handle everything else.
Thank you very much, Dr. Hintz. All right, so we've got quite a few questions that have come in here. Let's go ahead and get started with those. First, just piggybacking off of the last bit of your talk there, we had a comment from Franz Joseph Hamp, who said that he has a private observatory in Chile that he could use to study these stars, and he would be interested in the Southern Target List. I would like to add just a little bit to that question and say, could you please announce some specific directions for people like Franz Joseph who want to get directly involved with this? What should they do?
Basically, once we have the list, it depends on what equipment people have. If it's photometric, pretty much getting as much light curves, so as many nights in a row, as many complete light curves as possible. Multiples in a night are good. And filters, we can tend to work around a little bit. When you do the analysis, one thing you have to be consistent of is that you're in the same filter. But it's good to actually, if somebody's working in blue filters or red filters, to be able to actually do two separate analyses. So if somebody's got limited filters, or if somebody's got a nice setup and can do alternating like a blue and a red filter back and forth, that's actually really valuable. So a lot of it's going to be dependent on equipment, and I'm hoping when I put the website together to have some of the instructions of what's valuable in there as well.
Thank you.
Yep.
Now, we have a question here from Mel Blake, who had asked, how do you determine the times of maximum light? And that question was asked, I think, during Jarrod's presentation when he was talking about the school project.
Yeah, so there's two ways that we do this. So the first of them is using a program like Excel. You can fit the line and just find the maximum if you're just looking at like a single peak. What I tend to do is, if I have a large string of data that I've gotten with more than one maximum, I will fit it using something like Period 4 and Peronso, and then find more accurate times of maximum light using that. Because we don't have continuous data, we have like a data point every 5 minutes. We need to use something like that to be able to fit for the exact time.
Thank you. That's a good answer. All right. So we had two different questions come in that were asking about overtones. Here's one addressed to Dr. Hintz from Matthias Kolb, who asked if there's a physical explanation for why some stars pulsate in the first and second overtone, but not in the fundamental. And that this question was inspired because Matthias just finished his campaign on VZ Cancri and confirmed a ratio of 0.8 for the two main frequencies, which, as far as he knows, is a ratio of 2-to-1 overtones. So.
Yeah, it's been a while since I was working in those, and I used to know the answer to this, and I just can't bring it up off the top of my head. But there is some logical, because we do see that a lot in the structures of the stars, the light curve structure. It comes up with very specific ratios like he's talking about there. And for the life of me, I cannot remember it off the top of my head. I'll see if I can find it in my notes.
All right, thank you. So the other question regarding overtones was from Pierre Depontier, who asked if it's possible to tell from the light curve whether a star is pulsating in the fundamental or in the first overtone.
There is something about the shape that does indicate that. There's some older work by Harold McNamara that goes into that field in a little bit more detail. So I think some of the later papers he was publishing, I think, cover that. And again, I don't want to give a bad answer, and that might be a good place to look at, because he was very detailed in his work. So he would give a very detailed explanation. Publication. So those would be in the journals, I should mention.
Thank you. All right, we had a couple of different questions here about high amplitude delta Scooty stars. It was asked whether you, Dr. Hintz, also study those.
Yeah, when we look at the delta Scooties, I work on all of them. So by standard definition, anything above 0.2 is a high amplitude. Sometimes people get into the shape of the curve being the deciding factor for that. But so those are the highs. The lows are below 0.1. And I tried to actually call the ones in the middle between 0.1 and 0.2 the MADs, which is the medium amplitude delta Scooties. Mike Brager didn't appreciate that. He was the referee on the paper. Then the thing about it is the name is appropriate. The medium amplitudes are the ones that do absolutely bizarre things. They're like the most unstable bunch of stars. High amplitudes are fabulous. I love the high amplitude ones. A lot of the stuff on the Atlas list would actually be considered high amplitudes, which is a lot more than normal because usually the ratio that are found, and this scares me a little bit about the Atlas survey, they're finding predominantly high amplitudes. They're not getting the more common low amplitudes. And so it's probably something about their search algorithm, but no, I love high amplitude. Okay, first star I worked on, my undergraduate project was an SXV. So those that know what that is, that's one of the high amplitudes and the low metal content one. So the classic SX Phoenicia star. So that was my undergraduate project. So yes, I love high amplitudes.
Excellent, thank you. I'd like to add a comment to that, which is that I've recently seen some fantastic light curves created by visual observers of the star SX Phoen, and that's now on my bucket list to observe visually. I think it's very cool that you can see it vary over the course of a couple hours.
Yeah.
All right, and so another question about high amplitude delta Scooties from Richard Wagner. He asked, how do the high amplitude delta Scooties relate to regular delta Scooties in terms of the modes and number of frequencies?
Yeah, usually what you're seeing in the high amplitudes is, well, a lot of the high amplitudes, the classic ones that have the curves that look like classic Cepheids, classic Arlaris, is that sharp rise, slow decay. And that's basically the fundamental, and then the harmonics is what you need to fit it. There are some goofy high amplitudes that go the other way, slow rise, fast decay. Again, it's the primary and the harmonics. When you get into the lower amplitudes, it gets a little, the high amplitudes are radial or P modes. The low amplitudes are harder to deal with because sometimes you will get the G modes down there. And a lot of it is just, and this is something a graduate student of mine worked on years ago, was trying to figure out, even if a mode is driven in a star, how does it get to the surface? And, what does it take to actually see pulsations could be going on deep and not reaching the surface. And so some of it is structural, likely in the nature of why we only see the low amplitude versus the ones that are beautiful, high amplitudes being the beautiful ones. So it's probably something structural in nature. That's the difference between them.
Okay, thank you. All right, we had a question from Tim Stone who asked, do we observe any spectral variation in delta Scooty type stars, and are seismic features observable spectrally?
Yes. We do see, we get a couple of different things with the spectral features. One of them is obviously the radial velocity measurements. So we can get the radial velocity curve to go with the light curve, which is the classic inverse. So they look like an upside down light curve. There are also the line shapes do change during the pulsation cycle. And so that is some of the features of you'll see like the H alpha lines and stuff getting twisted a little bit. Most of the spectra I do are low res or lower resolution that can be used for other things. So one of the things I actually see in the lines is the the depth of the hydrogen lines changes during the pulsation cycle, so I can actually measure the temperature curve with a system that Dr. Joner and I worked on, Mike Joner and I. So we do see that. And the last thing we are going to work on here shortly on a couple of the brighter delta Scooties, high amplitude delta Scooties, is actually looking for the magnetic field effects to mess up the spectral. The way we measure the magnetic field is the distortion of the spectral line shape. So all those feed into the spectroscopy.
Thank you. That's a great answer. And that's made me actually want to ask one of my own questions about spectra. Is would the change in equivalent width of the hydrogen line be visible at a quite low resolution of like a slitless spectrum, say R500?
I haven't got down quite that far, but I think it would. Instead of actually trying to measure the line directly, you could also measure it with spectrophotometry and convolve some filter functions, and that tends to pull it out pretty well.
Thank you. And we have a question here from Shaimal Mitra. I apologize if I've mispronounced your name. Who asked if we can use delta Scooties as distance indicators.
Yes, they are. The trouble is, if you look at the luminosity in an HR diagram, Cepheids are big, bright stars, and we can see them way out there. We sometimes study delta Scooties in the large and small Magellanic Clouds because they give a good distance indicator to those. Because they're bright enough to be seen. But when we start getting out to something like, say, M31, okay, that's a little hard. And they're also not going to give you the James Webb for, hours on end to get a light curve of a delta Scooty. So that's where it kind of falls apart.
Mm-hmm. All right, thank you. And we have two questions here from Chuck Gorovic, who asked if you have developed any worksheets, materials, or handouts for teaching high school students about short period pulsators? That's the first question.
You want to cover that, Marcelo, or you want me to cover that?
Yeah, I'm working on it. I have some, I can't say good handouts, and I'm working on it. It's not a final version. We are all working on it.
And the one thing I'm hoping with Marcelo's help is to, when we have those handouts, is to have them translated so we can get them into a couple other languages to do a better job. Try to get over any of the language barriers we might encounter otherwise.
Excellent. All right, and the second question from Chuck was if you could provide a copy of your presentation, and the same thing to Mr. Hansen and Mr. Bighetti.
I can send mine to you. That's no big deal.
Okay. All right, then if and also Mr. Hansen and Mr. Bighetti, if y'all are okay with it, then you guys could all email me your presentations after the webinar, and I will arrange to have them emailed out to the participants. I think that's probably the best way to do it.
Yeah,
Right.
I'll send that to you.
Thank you. Okay, and that looks like that's it for our questions so far. So I'm going to go ahead and put up the closing screen here. Oh, there we go. All right. So first of all, I would like to extend a huge thank you to Dr. Hintz, Mr. Hansen, and Mr. Bighetti for sharing your time and knowledge with us today. I would also like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All-Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. the Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Today's webinar has been recorded, and the recording will be made available for free on the AAVSO's YouTube channel. Be sure to check it out. You can find a full library of webinars just like these there, not only from this year, but also we've got last year's up in a playlist. While you're there, please consider subscribing to our channel. Not only will you then get notified every time a new webinar recording is posted, but by hitting that little subscribe button, you will be increasing our educational reach by making YouTube more likely to suggest our videos to others. It's just one more way you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So please, if you're not a member, join the AAVSO. AAVSO membership comes with a wide array of benefits, including free access to our mentorship program. If you want to become an observer, but you're not sure where to start, our mentors can help you hit the ground running. If you are already an AAVSO member, don't forget to renew your membership. And of course, we would be grateful if you would consider donating to the AAVSO. Every donation matters and goes towards making programs like this come to life. As an aside, you will notice that on our end card now, we do have a QR code, that black and white box there. And if you hold up your smartphone, chances are, because of the whole creepy cloud connectivity of the day, it will recognize the QR code without you having to take a picture. You can tap on that link and it will pull up a page where, once it loads, here we go, you can donate directly to the AAVSO. You don't have to go to our website and try and figure out wherever the PayPal link is. And you don't have to have a PayPal account to do that. So it's easy for you. All right, one last thing before you go. After you leave the webinar, you will be automatically directed to a survey. Please do fill it out because we want to hear your feedback. You are more than welcome to fill out the survey, even if you've already filled out one in a past webinar, because we are continually reviewing the feedback after each webinar and using it to decide where the future of the webinar series will go. This is a great time to suggest topics that you would like to see in the future. Do note that the survey is anonymous. So if you want to receive a response from the AAVSO to any questions that you might happen to ask in the survey question responses, then make sure that you write down your email address or some way to contact you so that we can send our reply. Finally, I would like to extend one last huge thank you to Dr. Hintz, Mr. Hansen, and Mr. Bighetti from all of us at the AAVSO. We appreciate you.